Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Avrajit Bandyopadhyay with us today. Hello, Avrajit.
Hi, Frank. Thank you for having me.
Well, thank you so much for agreeing to talk about your very awesome article, which we'll get to here in a second. And Avrajit, what's your geolocation?
I'm currently in Gainesville in Florida.
Gainesville, home of Disneyland.
Yeah, close by.
Oh, very cool. And it is April 17th of 2025 as we record this. And is spring in the air in Florida? Have we turned the corner?
Yeah, it's spring in the air. It's cooler than what we expect. Like the mercury is hitting like mid 50s.
Okay. Okay. That is a little cool for Florida at this time.
Yeah, cool for Florida.
Yeah. So I'm in Phoenix, and we hit our first triple digit temperatures last week.
Oh,
It's cooler today. We're only into the 80s today. But yeah, we are warming up to uh, the broiler summer. It's coming.
yeah, the dreaded summer.
And Average, what's your position there in Florida?
Yeah, I'm currently a postdoctoral research associate here
Cool.
at University of Florida.
Very nice. Very good. And as a postdoc research fellow there or otherwise, what do you like to do for research?
Yeah, for research, I mainly focus and try to understand the older stars, the stars that are formed early in the galaxy, early in the universe,
Hmm.
and try to find signatures of what could have happened at that epoch during the early infancy of the evolution of the universe.
Very nice.
I look at stars like star clusters, dwarf galaxies, all structures that are old and retain signatures of the oldest stuff.
Very cool. Very cool. And that is going to bring us to this very awesome APJ supplement article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The R Process Alliance. Fifth data release from the search for R process enhanced metal poor stars in the galactic halo with GTC. And average it, take us away.
Yeah, thank you so much, Frank. So this is the fifth data release for the R Process Alliance, and I have done this work in collaboration with the R Process Alliance team. It includes Rana Izzadeen at University of Florida, Carlos Allende Prieto at ISC Canary Islands, Nima Arya, Shivani Shah, they're students here at the University of Florida.
Nice.
Tim Beers is again at University of Notre Dame, Anna
Mm-hmm.
Frabel from MIT.
Yes.
Therese Hansen, she's from the University of Stockholm. Erika Hombeck, she's currently at Lawrence Livermore National Lab.
Hmm.
Vinicius Placco from NSF NOAA Lab. Ian Roderer, currently at North Carolina State University.
Oh,
And Shirley M. Sakari at San Francisco State.
okay.
This is a big team of researchers who all are interested in studying the problem. What happened in the early galaxy to the how did the oldest stars form? And how did the chemical evolution of the galaxy, of the universe, took place the way it has taken? So here in this team, we have theorists, we have observers, we have people
Mhm.
who are working on simulations, and
Cool.
we try to look at a problem from holistically from the different angles to
Yeah.
understand the overall picture.
Very cool. Great shout out. Great shout out. Okay, let's go ahead and get into it.
Yeah, so to introduce like why we do this, because we know if you look at the night sky, we see a large number of stars, but we don't really understand how these stars are formed. So, as we go back in time, we see what are the initial nucleosynthesis channels that has taken place. The sun, as we know, are relatively a new star, and it is a product of several generations of nucleosynthesis and different generations of stars.
Mm-hmm.
And they all have contributed to the chemical picture of the sun. So
Okay.
as we go back in time, we find less number of contributions from different progenitor populations.
Okay.
So as we look back in time, there are two ways to do this. One is to look at the high redshift universe,
Okay.
go back in time and see the structures that are formed very close to the Big Bang,
Mm-hmm.
or look at our own galaxy where we get higher signal and try to find stars that are formed as early as the few billion years after the Big Bang.
Right.
So
Cool.
this is the approach we take because for our science, we need high resolution, like a good signal with a good signal to noise ratio.
Okay.
And for that, we need bright objects.
Yes.
And these stars in the outskirts of the Milky Way, in the Milky Way halo, provide us that opportunity to look back in time, find stars from the earliest galaxy, and still get a good enough signal to understand all the elements that are present right now in these stars.
Cool. I'm
And
with
since these stars are almost always low mass, the low mass stars are old enough to stay up to this date.
you.
And because they're low mass, they're still in the main sequence and they retain these elements that are formed during their birth. So when
Yep.
these stars were taking birth, they retain exactly the same signatures that were there several billion years ago and are still there, observable, waiting for us to look at those clouds.
Cool. Very good. I'm with you.
Yeah, so this is the main motivation for looking at the metal poor stars. Metal poor signifies stars that have less amount of heavy metals
Mm-hmm.
because the universe started with hydrogen, helium, and traces of lithium after the Big Bang, and
Yep.
all other elements beyond these three formed either within stars or in explosions in supernovae or other such cataclysmic events.
Okay.
As we find all these elements and their individual ratios, we do understand their original sites and where and how these elements are produced.
Okay.
For example, as I said, hydrogen, helium, and lithium are formed in the Big Bang nucleosynthesis.
Mm-hmm.
The oddsy elements like sodium, aluminium, the alpha elements, magnesium, oxygen, the iron peak elements, iron itself, cobalt, nickel, these all elements, most of them are synthesized in core collapse supernovae.
Mm-hmm.
The lighter ones, like carbon, nitrogen, oxygen, are produced in stellar evolution.
Yes.
However, the elements beyond these, the heaviest elements, like the elements formed by neutron capture methods,
Okay.
they are produced only in like most energetic processes, like let's say neutron star mergers,
Okay. Okay.
collapsers, or black hole neutron star mergers.
Mm-hmm.
And when, like,
No problem.
let's say several decades ago, when people looked at the spectra of the stars in more detail at higher resolution, they noticed a pattern for these heavier elements. No
Mm-hmm.
matter which star you look, the pattern is always same for
Yes.
elements heavier than the iron peak.
Yes.
If at the sun, at the older stars, any star anywhere in the galaxy, that pattern seems to be universal. So
Mm-hmm.
that came to be known as the universality of our process.
Okay.
And we have no idea. We are starting to get an idea, but we still really don't understand what caused that pattern that is so universal, so robust in all the stars.
Very nice. Very, very.
And to detect that pattern, to detect all the elements producing that pattern, we do need bright stars and very good signal to noise ratio. And
Mm-hmm.
that's why we could not get a large number of these stars in the early efforts of stellar spectroscopy.
Yes. Okay.
And that led to form this global alliance called the R-Process Alliance, which tries to find such stars that are enhanced in R-Process elements. These
Mm-hmm.
enhancements in R-Process elements for a statistically significant number of stars are important to understand the sites of their production, and not only the sites of the production, like the mechanism of the production, the temperature, the pressure, the nuclear reactions that are responsible for their formation.
Yes.
So this process started after the gravitational wave in 2017.
Yay.
And fortunately, after the gravitational wave, the monitoring of the kilonovae showed us that yes, our process is conclusively produced in neutron star mergers.
Okay.
Like they could detect an element called strontium that is produced via the rapid neutron capture process.
Mm-hmm.
So yes, that conclusively showed neutron star mergers is certainly one of the sites producing our process. But
Okay.
questions remain. Is it the only site?
Yes.
Could it be formed early enough in the history of the galaxy to show these elements even in the older stars? Because stars take time to form neutron stars and then form a binary neutron star, and then that orbit to march together to collide and form the ejecta. So even stars that are formed before this time scale could happen, they show signatures of our process.
Right.
That leads us to the question, like, what are the other sources for our process? And if there are multiple sources, how do you find the same universal pattern for our process?
Okay. Right. Right.
With these questions in mind, this collaboration called the Art Process Alliance collaboration started to gather data. They used like several high resolution spectrographs, both in the north and the south. This paper here observes data from the Gran Telescopio Canarias in
Mhm.
Canary Islands, and this is the fifth data release. So here we mainly target stars in the north. Uh, if you could scroll down to
Oh,
the
sure.
figure one.
Yeah. Okay. We're going to get into the observations. Figure one, V band magnitude.
Yeah. So we observe the stars with the Gran Telescopio Canarias. It's one of the like largest aperture telescopes in the world right now. And
Mm-hmm.
because of that, we could really probe fainter. The previous Art Process Alliance results look at slightly brighter stars in order to get good signal to noise, but we had the luxury to go even fainter up to 16th magnitude.
Nice.
And this ability to probe fainter to the 16th magnitude, I,
Nice.
we believe would help to find stars that are further away from us or slightly less brighter, closer to the
Right.
turn of main sequence.
Right. Okay. Cool.
And
10, 20, 40.
scroll down to figure two.
Okay. Looks like we got on the order of 10. We've got about 50 of them, roughly.
Yeah, we'd roughly have around 45 stars, but out of those 45, we could had to discard three because of poor signal to noise ratio
Ah,
and do
okay.
our science with the 42 of those.
Target stars in table one, people. And figure two, radial velocities. Okay.
Yeah, so after gathering the data with the Gran Telescopio Canarias, we used the pipeline developed by Carlos Arjen de Prieto for reduction of this
Cool.
observed sample. And we used spectroscopy made harder to analyze the data. And finally, after reduction, we find that only three stars in this entire sample showed signatures of binarity. So we here compare the radial velocities
Okay.
derived from the spectra with the radial velocity coming from Gaia.
Okay.
We show a peak close to zero, which is what we expect, like it's
Mhm.
consistent, but there are deviations that go to as high as like 10 kilometers per second.
Yeah.
These are potential binaries that could be traced. However, the word of caution is this binary has not got anything to do with our process signatures, as most of the our process enhanced stars we find are not really binaries.
Right.
This is just a take that we need to probe more into these three binaries, like take multi-epoch observations to model the binary orbits and to see what is the periods and whether there is a mass transfer that could have happened from its binary component.
Yeah, yeah. Mm-hmm. Yes.
And I think we have scrolled past the table one, so that contains the target selections.
Yes. We went through that. So that's target selections. People want to check that out. Check it out.
Yes. So
RV
here we
guide.
have the magnitudes, exposure time, the SNR. So we aimed for SNR greater than 20. And since it's
Okay.
a snapshot survey, so in GTC we have this filler proposal. So wherever there is a gap between two planned observations,
Okay.
they need some time to switch between two observations. They take the time to observe such stars that are bright and readily available. So
Okay.
we built in this proposal long ago, like let's say 5 years ago, and we got like around this number of spectra from those filler proposals.
Very nice. Very nice. Good signal to noise there. Fine. Table one. Figure two we covered. So now we're going to get into some of the elements, I guess.
So we will also show the HR diagram in
Oh, I'm sorry.
and the metallicity distribution in
Figure three, yeah. Okay, atmospheric parameters, figure
yeah, stellar
three.
parameters are up there in that table. We'll come back to it, but for now, like here again, we see the metallicity distribution for these stars is slightly shifted towards the metal poor end. The peak of the metallicity distribution for this
Yep.
fifth data release is slightly shifted towards the more metal poor end. However, it doesn't the tail doesn't extend as far as like the earlier data release. So this is a more clustered sample with
Yes.
a tail more towards the solar metallicity, like which they have three stars. greater than -1 FE/h.
Right here.
But
Yep.
most of our stars, yeah, right here. And most of our stars are clustered around FE/h -2.85.
Yeah.
So
Yeah.
we get to probe. So FE/h -2.85 is very close to like 10 to the stars that are having less metals than, like, how do I say this? Stars with less than 10 to the power 3 times the metal that of Sun.
Yes.
Like Sun would have 10 to the power 3 times more metal than these stars with metallicity of -3.
Factor of 1,000.
This is in the logarithmic scale.
Yes. FU over H bracket. Bracket notation.
Yeah.
Take the log. Mhm.
Yeah. And in figure 4, we show the HR diagram.
Ooh,
So in HR diagram, we have isochrones for
okay.
different ages taken from Marigo et al. That considers like, well, that has the thermally pulsating AGBs as well as the alpha enhancements that we find for halo stars. So
Yes.
these are the tracks for the isochrone, and this is the scatter that we find for the given sample in terms of effective temperature and log G.
This is for metallicity of -2.3. Okay. hmm
Yeah. And
hmm
all the stars are color coded by the metallicity. Yeah.
Okay.
And if you could scroll up to the table 2 where we discuss the stellar parameters.
Okay, I'm just absorbing this one a second. Okay, I'm good on that one. Okay, table 2, atmospheric parameters.
Yeah.
EFF, G, turbulence.
Yeah. So here we list the individual stars that we observe here and with their local thermodynamic equilibrium parameters. And we invoke we don't invoke the non-LTE corrections directly. We apply a correction factor to the
Yeah.
derived LTE parameters.
Mhm.
So these corrections comes from several reasons that are like go. One of them is non-LTE corrections. So these corrections were to go up.
Yeah, we got the equation. Here it is. Or T effective correction.
Yeah.
hmm
So how we do this is we derive that T effective LTE based on iron 1 and iron 2 lines. So
Okay.
if we get to the local thermodynamic equilibrium at the effective temperature, the iron 1 and iron 2 lines should not give a trend. So
Yes.
there should be a flat line without a trend, and iron 1, iron 2 should give the same abundances for iron.
Yes.
So we invoke this property to derive the effective temperature and the corresponding log G.
Okay.
And also we invoke that there shouldn't be trains with a reduced equivalent widths.
Yes.
So with that way, we derive the microturbulent velocities.
Okay.
Once we do that, this is the correction factor introduced by Anna Frebel in her paper in 2013, where she describes how to get the corrected temperature scale. So here, the corrected temperature imply temperatures corrected by a photometric calibration scale.
Okay.
Photometric temperatures, thanks to their good precisions, are provide a better estimation than the spectroscopic temperatures.
Okay.
So we calibrate the spectroscopically derived temperatures to a photometric scale. And then with the newly derived temperature, we again invoke the ionization equilibrium for iron 1, iron 2 lines
Yes.
to get the log G and the corresponding metallicity.
I'm with you. Cool.
So that is listed in table 2.
Yes, let's slide down to table 2. These are the corrected values based on that procedure. Okay.
Yeah. So on the left, we have the LTE parameters, and on the right, we have the non-LTE parameters. I'm sorry, the corrected LTE
Corrected
parameters.
LTE. Right.
Yeah. And we also note the number of lines we have used, iron 1 and iron 2 lines that we have used for these stars. And all of them are like around close to 100, or for the fainter ones, they're close to like 70 or 80. So
Good.
there,
Okay.
the statistical uncertainties is of the order of less than 0.2 in most cases, or
Yeah.
mostly around 0.2. So
Mhm.
which is within the observational uncertainties.
Nice. Very cool. Very cool. Good set. Okay. I'm good. Onwards.
Yeah, now we come to the abundances. So the
Okay.
reason why we're doing this is to derive the individual abundances of all the elements that are present in these stars.
Yes.
The studies that are trying to understand the origins of our process often focus on only the neutron capture elements.
Yes.
However, the other elements from carbon to zinc, they play a very crucial role.
They do.
we need the abundances for alpha, iron peak, and light elements to constrain the other sources that are not directly contributing to the R process. For example, core collapse supernovae. That could be constrained by alpha, carbon, and iron peak elements. And
Mm-hmm.
if we have a rough estimate for the mass or the energy of the core collapse supernovae that are contributing to these stars, we would be able to either eliminate them or include them in the calculations
Gotcha.
for the fractions coming from core collapse supernovae.
Okay.
So it's always important to find as many elements as we can because these individual precise patterns for all the elements, they tell us what were the exact sites that contributed to the buildup of these stars.
Yes.
So in the figures, like figures 5 onwards, I guess.
Okay, let's go to figure
No,
five.
figure 5, we
So
show
that's
the
synthesis.
spectral synthesis for carbon. So
Okay.
how we derive the abundance of carbon, this is an example. So black dots are the observed spectra, the actually observed spectra from the GTC,
Okay.
and red are the spectrum that is synthesized to model the what could be the abundance for carbon based on the CH molecular band.
Yes. Okay.
The
Mhm.
red gives the best fit. Blue and green are deviations by zero point 0.2 dex.
Okay.
Yeah, 0.25 dex. And black line is the line we would get if the spectra has no carbon.
Carbon.
So if
Right.
there is no carbon, we should just get the black line on top.
Yes.
And as we increase the carbon iteratively for the given stellar parameters like temperature, log G, and metallicity, we
Mm-hmm.
find this blue, red, and green lines. And the line that matches best with the minimum chi-square residue gives us the best fit abundance for carbon.
Okay.
And we have here one star that is enhanced in carbon, the other that is carbon normal.
Let's see. Oh, yes. Okay.
You
Uh-huh.
see the star enhanced in
Yeah.
carbon at the bottom is
Yes.
have a deeper molecular band than the one at the top.
Okay. All right.
So this is how we do, this is called spectrum synthesis, and this is how we measure the
Uh-huh.
individual abundances for the elements that we put in this study.
Cool.
And the corresponding distribution of carbon for all the elements is shown in figure 6.
Okay, so we go through the spectral analysis. Then we can do C over FE. Okay. Okay.
Yeah, these all these filled red stars are stars. Any colored filled red stars are stars from the study. And
Yep.
here we put in different colors to denote the different stars that we could find. We find stars escaping from globular clusters shown in green. We
Yes.
find magnesium poor stars in blue. We find R2 stars. R2 stars are stars that are significantly enhanced in R process elements.
Okay.
They're called R2. And R1 stars that are mildly elevated in R process elements.
Okay.
So we are going to carry forward this nomenclature for all the figures that we find in this paper.
Okay. So remember that. I'm with you. I'm with you.
Yeah,
Okay.
so here we find the R2 star, one in purple, is very like depleted in carbon abundance
Mm.
and this is also very metal poor.
Mm. Yes, it is.
And
Okay.
most of the stars in this sample fall within the observed scatter for other. So here, for a reference, the gray dots, they are the study by Ian Roderer 2014, David
Okay.
Young 2013, and Rana Isdin 2019. So
Okay.
they are around like 500 stars of similar metallicity, and they all have a very homogeneous analysis, very similar to the methods we use here. So there is observation. There could be some systematics, but we don't expect it to be significant enough to alter our results.
Okay. Very cool.
And in the subsequent figures, like we show the distribution for the derived abundances for our elements compared to the stars from the archive based on these papers.
Okay. Cool. And what is the horizontal blue line? It points.
Yeah, so the horizontal blue line on the top at carbon by over Fe 0.7, that kind of distinguishes the carbon enhanced population from the carbon normal population.
Okay.
So any star with an enhancement of carbon above 0.7, we call them carbon enhanced metal poor, CEMP stars.
There you go. Okay.
And we find 5 of them in this study.
1, 2, 3, 4, 5. Yes.
And the region between the two dashed lines, that is like the expected carbon, C over Fe close to solar values. And
Mm-hmm.
the ones below the black dotted line is the ones that are lower in carbon than what we expect from the nucleosynthesis for their metallicity.
Okay.
So both like below and above these dashed lines are the ones that are regions of interest.
Yes. Very cool. Good. Great plot. Okay. Onwards. That's carbon. And should we do some
And in figure
oxys?
7, again, we show a similar plot for sodium and aluminium.
Mm-hmm.
Sodium and aluminium are odd C elements, and they owe their origin could be from core collapse supernovae, could be from depending on the what kind of odd even what kind of pattern we see. That could be even from pure instability supernovae, but we haven't been able to conclusively tag down upon their ratios. And
Right.
also, a word of caution is these two elements, sodium and aluminium, have very high corrections for non-LTE effects.
Yes.
So it is very important to include the non-LT corrections for sodium and aluminium. For aluminium, they could be as high as 1 dex.
Oh yeah. Oh yeah. Okay. Interesting. Hmm. What do we got? Where did I miss this one? What are the black triangles? We've
I'm
got
sorry.
black triangles. What are the black triangles? We got one, two, three, four, five, six, seven.
Black triangles are the upper limits. There are
Got it.
certain stars for
Okay.
which we could not really derive the abundances. And there we try to derive an upper limit.
Got it.
So these are all like not measurements, these are upper limits for
I'm
these
good.
stars.
I'm good. Thank you. Okay. Doo-doo-doo-doo-doo. Got a couple. Got a couple with a lot of aluminum. Okay. Very cool. Okay. I'm good.
And in figure 8, we have like for the figure 8 we have for the alpha elements
Okay.
again. So
This.
so alpha elements are are the elements that have atomic number in multiples of 4.
Mm-hmm.
So they
Okay.
proceeds the nucleosynthesis chain by colliding with an alpha particle, and that process goes on. So like oxygen, magnesium, calcium, these are very well-known alpha elements.
Mm-hmm.
Silicon and titanium is an element shown on the right bottom panel that mimics the distribution of alpha elements, but it's not a pure alpha element.
Correct.
However, since its behavior is similar to alpha element, we include this in the figure of like alpha element abundances. And for halo stars, they all are elevated to close to zero point 0.4 dex,
Yeah.
usually.
Right.
And we find a similar trend for like most of the elements here. Of course, there is a significant amount of scatter, and we find a slight enhancements more than what we would expect for silicon.
Yeah. Okay.
And like you find stars here, like silicon close to like 1.2 or
Yeah.
1.1.
Yeah. Got them way up here. Mm-hmm. Mm-hmm. Then we got some enhancement on this one star here on this that must be the GC Escapee, yeah? It's got
Yeah,
a lot of titanium.
the titanium.
Uh-huh. Uh-huh. Well, that's interesting. Okay. Good. I'm with you. And figure 9, we go
And
into
again, figure 9, we talk of the distribution for the iron peak elements.
okay.
Iron peak elements are again mostly synthesized within the complete and incomplete silicon burning during the explosive phase of a core collapse supernovae.
Yes.
And the individual abundances of these elements tell us exactly at what region of the core collapse supernovae could be the dominating contribution for these star are coming from.
Mm-hmm.
For example, like the significant scatter that we see in vanadium.
I was gonna say.
Vanadium is an element that is very sensitive to the initial mass function. So if there is a large discrepancy in the masses of the progenitor supernovae that is contributing to the gas clouds that's forming the
Oh,
stars,
okay.
that would show a significant dispersion in vanadium and scandium.
Okay.
On the left, we find scandium. The next figure, we find vanadium. So the
Mm-hmm.
spread could be signifying that our sample has contributions from a wide range of supernovae mass.
Okay.
Similarly, manganese and chromium are coming from incomplete silicon burning. Cobalt and nickel are coming from complete silicon burning.
There we go.
So, so the ratio between these elements again tell us like what could be the mass of the supernovae that could produce the ratios that we see.
That would be cool.
Like again, nickel usually tracks iron very closely, and we see the scatter is like minimal for nickel.
Yes. Okay, that's good. And we go
It's not very
beyond.
straightforward to measure copper. We could find only like
Yes.
four stars with copper
Yes.
and be happy with another three or four upper limits.
Copper's tough. Okay.
Yeah. And zinc is again a very crucial element that has significant contributions from massive core collapse supernovae and as well as hypernovae.
Okay.
And zinc are usually like supersolar. They all have abundances greater than zero.
Wow.
And we
Okay.
find a similar trend for our stars. So our stars could, yes, have contributions from hypernovae.
Uh-huh. Uh-huh.
And see, like the interesting thing is the R2 star in violet here, in purple here, they
Yes.
have a zinc abundance of close to plus 1.3.
It's huge.
So that is like very interesting.
Well, it's enriched in zinc. It's enriched in vanadium. It just generally sticks out on those two. Okay.
And it's significantly depleted in carbon.
Uh, let's go back to carbon. Let's go back. Yes. Ooh, yes. Mm-hmm. Indeed.
So that makes it a very interesting candidate to understand what type of progenitor could it have come from.
Yes, that is an interesting one. Okay. Very cool. Nice distributions. They're beautiful. Okay. Now let's go beyond the Iron Peak.
Yeah. So then we come to neutron capture elements, elements that are formed by capturing neutrons instead of the usual proton capture reactions. So
Mhm.
this includes for this stars using GTC, we could find abundances for strontium, barium, and europium. These are the strongest lines that are there in the optical spectra.
Okay.
For there is a requirement to measure all other at least several other neutron capture elements, but for that we need much better signal to noise ratio in the blue and
Okay.
higher resolution.
Okay.
So
Okay.
here in this study, we try to constrain the sites based on the strontium, barium, and europium abundances. And in this figure, we find how we do that. Like we measure, again, very similar to the carbon plot I explained earlier. This is for three different stars. On the top, we have R2 stars that are much enhanced in neutron capture elements.
Yes.
Middle is R1, mildly enhanced. And
Okay.
bottom is an EMP that is not enhanced in our process elements.
Extremely metal poor. Okay.
Yeah. And we have strontium on the left, barium on the middle, europium on the right. And
Mm,
you can see how the lines
okay.
slightly like for R2, the lines are the strongest. And for EMP, the lines are the weakest.
Yes. Yes. Okay.
And
Uh-huh.
you can easily understand like how much the noise is contributing if you look
Okay.
at the R1 star for europium at the right, like on the right middle column,
Mm-hmm. Right.
with the
Middle.
right to it. Yeah.
Yes.
No,
Okay.
here like for the europium over Fe plus 0.4,
Mm-hmm. Mm-hmm.
the signal to noise is really not easy to constrain here. So
Okay.
the red line is again the best fit that we can get to these measurements, and
Yes.
green and blue are deviations, and black is the line we'd get if there is no element detected in the
Of that
spectrum.
one. Right. So it would be flat as you go across. There's your
Yeah.
baseline. Okay. Cool.
So, and it's always important to measure neutron capture elements using spectral synthesis as there are hyperfine transitions
Yes.
that would not be taken care of while doing an equivalent width analysis.
Fair enough. Mm-hmm.
Yeah. And
Mm-hmm.
also, these lines are often distorted and broken, and it's not straightforward to get like very clean lines.
Yeah, these are very pretty ones. Yes. You have to disentangle it from reality when you actually measure it.
Yeah.
Yes. Yes. These are synthesized. Yes. Okay. So we got our distributions of those three elements and how the lines vary. And Then we see how we do.
And this is how the sample spans out in the strontium, barium, and europium space. So again, the for the europium panel, the yellow broken line at the top,
Yes.
any star above that line is considered a R2 star.
Okay. Ah, okay.
And between the yellow and the blue line, that's an R1 star.
Okay.
Anything below that is a star that is non-enhanced in our process.
Okay.
So this is the current nomenclature based on the close to 100 star that we have now for
European.
stars significantly enhanced in our process elements.
Yes. Okay. All right. Let's see. Do. Okay.
And also like
Mm,
these elements have all their sources. It's not necessary that all these elements are coming only from our process. Strontium, barium can have their origins in S process, both the weak S process and the primary S process.
yes.
However, at very low metallicities, it's unlikely that the S process is contributing as much as the R process. The
Uh-huh.
contribution of S process sets in at metallicities higher than at least minus 2.5.
Right. Where you have enough seed material to generate those neutrons. Mm-hmm.
Exactly.
Mm-hmm. Yep. Very.
But however, europium is like a bona fide true indicator of our process at irrespective of metallicity until you get to like more than minus 1.5. So
Mm-hmm.
that is a reason why in the europium plot you see a red star at solar metallicity of minus 0.5. That is enriched in europium, but it's still not considered an R2 star
Because the metallicity is too high.
because its metallicity is too high and
Yeah.
it's very difficult to disentangle the true art process signatures from the other processes that have contributed to it.
Right. Ew, strontium to barium. Okay. Yes. Dot.
And
Yeah.
now strontium to barium shows a very high dispersion.
Yes.
So strontium is a light art process element, barium is a heavy art process element. So
Mm-hmm.
ratio of strontium to barium tells us like what could be the intrinsic differences between the sources that contribute to it. And
Okay.
this large dispersion tells us that there is a variation in the primary sources that contribute to these elements.
Okay. Cool. Nice. Very good. Okay. I'm with you on Beyond the Iron Peak. Okay. Uncertainties. Shall we
Yeah,
cover that or classifications?
yeah. Table three is where we say the uncertainties for the calculations, and
Mm,
we assume a difference in the temperature, log G metallicity, and propagate it along the calculations to derive at the final observational uncertainties at the right column. And
mm,
they all are close to around 0.2.
Pretty good deck. Yeah. Mm-hmm. Mm-hmm. That's good. That's good. Very nice. And this T effective is after the corrections. Mm-hmm.
Sorry,
Okay.
yeah, this T effective is the corrections factor of 150 Kelvin.
Mm-hmm. Mm-hmm. Right. Okay. Very cool. Okay. And then we got some abundances selected.
Yeah. And table four, we have the most important elements for this study, like carbon, magnesium, strontium, barium, europium, and finally barium over europium and their corresponding classification. Now, why barium is europium is important is because barium is an element that is well known to come from S process. It's an indicator of S process at
Yes.
slightly higher metallicities. However, europium is a pure R process.
Okay.
So at a little higher metallicity, how do we differentiate the R process from the S process?
Yes.
That is done with a ratio of barium over europium.
Okay.
So if barium is much higher than europium, it's likely to be a S process origin. If
Okay.
europium is much higher than barium, it's certainly an R process origin.
Like this
And
one.
we use that criteria to classify stars as R1, R2, extremely metal poor.
Very metal poor.
Very metal poor is stars that are metal poor than Fe over H minus 2.
Mm.
Extremely metal poor EMP is Fe over H minus 3.
Okay. Okay. Thank you. Okay. Okay. Very good. I'm with you here. Nice table. That's great. Okay. So we got all those elements. And we got some of the
Yeah.
properties of the lines.
And here we put in like all the line properties that we
Great.
use. This is compiled using line make, and there is that our process aligns line list. Line make is an online tool. It's a tool provided in GitHub by Vinicius Blacko et al.
Okay. Okay.
So we could find the wavelengths, the log values precisely from this tool.
It's also in machine readable form if you want to grab it from there and you can process it accordingly. Very cool. Lambda chi, log G, equivalent width here. What does A of X remind me? Abundance?
This is the absolute abundance,
Yeah.
that is like the log epsilon abundances in the logarithmic scale.
Yes. Okay. Good. Nice. Beautiful. Okay. Table 5, those are lines. And then we get into some.
Yeah, before getting into the results, like this next figure there, we show that comparison of our derived abundances.
Okay, so we got
It's a little
some
bit
light
better.
element abundances here in table 6, iron peak in 7. And here we go. Compare
Yeah,
derived
the
abundance.
figure on the top. So here we have a star in common that was also started in our PA data release 1 and 2.
Okay. Use our
And
color.
here uh, we show the differences in the measured abundances for all the elements from carbon to europium for these three studies. And we find that differences often are within the observational uncertainties.
Mm-hmm.
However, there are slight deviations for silicon and chromium.
Okay.
The main reason coming for this is there is a difference in the derived stellar parameters, and there is a difference in the resolution of the optical spectra.
Between the
So
two
when we
studies.
do that, the abundances for these elements are more sensitive
Ah,
to the temperature of the derived temperature of the stars. So if there's a difference of 100 Kelvin, the abundance can slightly vary to as high as zero point 0.2 dex.
okay. Okay.
So there we find a slight difference between these two, but most of the elements do agree in the derived abundances.
Mm-hmm. Very good. So we have some consistency. Yay. Okay. Let's figure 12. And then should we go?
Yeah, so now that we have listed classified all the stars in this study,
Okay.
and we have shown the tables uh, containing the abundances for the light elements as well as the iron peak elements, it's the time to see why we measured the elements. Now
Okay.
that we have observed the stars, we've measured the elements, and what do we learn from measuring the abundances of these elements?
Nice.
So
Okay.
this is a figure that uses iron peak elements and the alpha elements to try and trace the mass of the progenitor supernovae.
Ah, okay.
On the left, we use manganese and chromium.
Yes.
So
Okay.
manganese and chromium, both the elements are formed within the incomplete silicon burning region of a core collapse supernovae. And as we find a correlation, like if you see the literature data that is shown in the form of a density plot, they all are elongated along the diagonal of this figure.
Yeah, right. Mhm.
Yeah. So
Mhm.
this elongation implies there is a correlation
Relation.
between manganese and chromium. And our samples shows that there is this correlation. So where do we expect this correlation? We expect this correlation only if these elements are synthesized at the similar region of a supernovae.
Yes. Okay.
And for a similar region of a supernovae, that is the incomplete silicon burning in a core collapse supernovae of mass less than 80 solar mass.
Okay.
If the mass of the progenitor supernovae exceeds over that, we don't expect to see a correlation between these two. What we get instead is called a pair instability supernovae that
Yes.
would give an odd even pattern well beyond even the odd Z elements.
Yes.
So in this figure, we get a rough estimate that yes, it could be core collapse supernovae
Mhm.
mass less than 80 that is contributing to the stars we see here. On
Okay.
the right, we use the alpha elements. So calcium, silicon, and titanium form a group of alpha elements that is formed in less massive core collapse supernovae or called explosive core collapse supernovae,
Uh-huh.
whereas magnesium and oxygen are formed in hydrostatic core collapse supernovae
Okay.
that is more massive. So we try to
Okay.
compare these two sets of alpha elements,
Where's the
and
thing?
we call them, the problem is we could not detect oxygen in the spectra. So we have to do with magnesium as the only representative of the hydrostatic alpha burning. So
Okay.
here we take the difference between the explosive and the hydrostatic alpha burning on the right,
Effectively.
call them delta alpha, and
Uh-huh.
plot them as a function of magnesium.
The light one.
And the
Okay.
color bar is the metallicity of the stars,
Hmm.
and they fall along linearly.
Yeah.
However, the metal-rich stars cluster around the top left of the figure. So
Yeah.
this indicates that as delta alpha goes upwards, that is, as the explosive alpha starts to dominate, that is where we find signatures of type 1 supernovae, and they are also primarily metal rich.
Mm.
However, as delta alpha goes negative, the hydrostatic alpha takes over, and we also find it also associates with increase in magnesium. So as magnesium is higher, delta alpha is lower, it's the hydrostatic alpha burning that dominates. And to add to it, we also added masses of core collapse supernovae in the colored triangles
Mm-hmm.
and the hypernovae in the colored squares, colored to the metallicity on the right.
Oh, okay. Okay.
So it indicates that the core collapse supernovae and the hypernovae are more clustered towards the bottom right,
Yes.
whereas the type 1a supernovae are clustered towards the top left.
Yes.
So
That
this
makes
gives us a precedent for understanding, like looking at the alpha elements, we can see what region of this linear relationship that it falls into and classify them as potential progenitors type 1a supernovae or massive core collapse supernovae with possible hypernovae contributions.
very cool. Very cool. Okay. Mm-hmm. I'm with you. Yes. Okay. Beautiful.
Yeah, and so now that we know that core collapse supernovae contributed to these stars, it's time to see how the R process correlates with core collapse supernovae.
Okay.
And that we will see in the next figure, figure 14.
Sites of the evolution. Okay. Distributions. Okay. Let's blow that up a little bit. Okay.
Yeah, so magnesium, so let's look at the left figure first.
Okay.
Like magnesium is an element coming from core collapse supernovae.
Yes.
Europium is a pure tracer for our process.
Okay.
We try to do magnesium over europium, that is core collapse supernovae over neutron star mergers, if europium is
Okay.
coming from neutron star mergers.
Thank you.
Let's not assume that. Let's say our process.
If, okay. Fine. Okay.
Yeah. And here we plot three different groups of stars. In the purple, we have R2. This is all R2 that we have studied till date from the R Process Alliance, including all the data releases so far.
Yes. Okay.
And green are the R1 stars.
Okay.
And and the gray dots are the non-R process enhanced stars in this figure. And on the right panel, on the right of the same panel, we show the histograms for their distribution
Bang, bang, bang.
over magnesium over europium space. And
Okay.
we find that non-RPE stars peaks at a different value than the R process enhanced stars.
Uh-huh. So they do.
Especially R2 stars peaks at a much lower value.
Yes.
And
Okay.
previous studies showed that magnesium over europium is generally flat for galactic stars. However, if you take out the non-RPE component, if you take out stars that are not enhanced in our process,
Okay.
we find a definite slope in magnesium over EU,
Mm-hmm.
both for R1 and R2 stars. And
Yes.
the slopes are very similar.
Mm-hmm.
What does this tell us? This tells us as the galaxy or the universe gets older, like metallicity, as the universe gets older, metallicity rises.
Yes.
As metallicity rises, europium increases more than magnesium.
Okay.
Magnesium is coming from core collapse supernovae.
Okay.
But however, with the aging of the universe, we find more europium in stars than magnesium.
Okay.
So there is a rise in our process as the universe gets older. So there has to be a secondary source that's contributing towards the buildup of europium with the evolution of the universe. However, even at the earliest epochs of the universe, we do find a certain amount of europium.
Yeah.
So that must be coming from a different source. And that cannot be core collapse supernovae because Magnesium is the like a primary contributor of core collapse supernovae. Yeah, let's take to
Okay.
understand what is the contribution of core collapse supernovae. And here we find a rise of europium compared to magnesium.
Mhm.
And
Mhm.
also the R1 and R2 stars, the R1 and R2 star peaks at different magnesium over europium. So R2 stars peaks at different europium than magnesium.
Okay.
However, the spreads we see for R1 star is much lower than R2 star. That is because of a definition of how R1 and R2 are
Yeah, it's
defined.
just a narrower band, whereas the
Yeah,
other one is
R1 is
wide
a very
open,
narrow band and R2 has like much wider
wide open.
distribution.
Uh-huh.
However, the main takeaway from here is the downward slope once we take away the non-RP stars from this sample. If we
Okay.
consider all the stars here, we do not find any slope here. Like you see,
Okay.
the non-RP stars peak at magnesium over europium at 0 in the histogram here.
Yes.
That's exactly the peak you will get even if you combine all the three samples. But the
Yeah.
moment you take away
Okay.
non-RP, you
Yeah.
find a different distribution.
Interesting. Cool.
And on the right, we use the strontium, barium, and europium.
Okay.
Because strontium again is the lighter R process,
Yes.
barium and europium are heavier R process. How
Mm-hmm.
we compute this quantity, strontium plus barium by H is given in the footnote below. So it's like a simple logarithmic scaling reaction.
Yep. Got some log of some epsilons. Here's
Yeah.
the
So
definition. Yep.
use
Yep.
this relation to compute this quantity.
Okay.
And there we again find an offset between R1 and R2 stars.
Indeed.
Green is R1 and purple is R2. And at europium over H greater than minus 2.5, this offset tends to increase. So we try to compute a theoretical, as more of a simulation of galactic neutron star mergers and their
Okay.
expected distribution.
Okay.
So the black solid line showed here, that is what we would ideally expect from a neutron star, galactic neutron star merger. And it falls very close to a R2 stars distribution.
That's done. Well, that's encouraging. Okay, very good.
Yeah, so it could be that neutron star mergers are a major component for R2 stars, but there could be additional sites that are contributing or rather diluting the effects of R2 star of
Right.
these in the R1 stars. And that's why we get a lower europium in R1 than R2 stars.
Yes. Yes. Okay, that hangs together. Very cool. Okay. Good story. All right, I'm good. Okay, onwards. Yeah, we did have that globular cluster escapee there, didn't
Yeah,
we?
and finally we have the globular cluster escapee.
Mm-hmm.
So why this globular cluster escapee is very important is because we know the globular cluster metallicity doesn't extend beyond Fe over H minus 2.5.
Yes.
That is the well-established metallicity floor for globular clusters.
Mm.
However, recent studies, for example, like 2 years ago, Martin et al. In 2000 found a C19 stream across the galaxy that
Mhm.
has found disrupted members of globular clusters to as low as minus 3. Similar work by Federico has found stars that are lower than globular clusters, metallicity in the galactic halo. How we tag these globular cluster escapees in the halo is given in the next figure.
I think it's gotta
We
be.
so
Okay,
so
gotcha.
second generation globular cluster star show an anticorrelation in the lighter elements
Ah, aluminum to no
like
sodium. Yes, yes.
sodium, aluminium,
Uh-huh.
magnesium. They
Uh-huh.
show this is called light element anomaly. So
Okay.
here we find stars in globular cluster second generations are elevated in aluminium as well as sodium. This is a signature used to identify potential globular cluster members.
Okay. Mm-hmm.
So the
Okay.
stars shown in blue here, blue are actual globular cluster measurements,
Yes.
black are halo stars, and
Mm-hmm.
the one in green filled stars to the right bottom of the globular cluster population is the star that we tag as potential globular cluster escapee.
Gotcha. Mm-hmm.
However, to note here that we find stars in red filled circles, red filled diamonds
Yes.
next to it, as well as just beside the blue globular cluster population that
Mm-hmm.
is even higher enhanced in aluminium. However, they do not show all the signatures of globular cluster enhancements. Like they should show a
Yeah.
CHCN anomaly. They should
Yes.
show sodium oxygen anticorrelation. that
Yes.
should show a magnesium aluminum anticorrelations. Just having elevated aluminum and slightly elevated sodium is not a true diagnostic for a globular cluster escapee. We
Fair.
need to look at all the signatures, and after looking at all the signatures, this one star in green stands out to be showing consistent abundances with globular clusters.
Okay.
Then in the right panel, we plot individual stars of like metal poor globular clusters
Okay.
here, and the green star here falls within the globular cluster population.
Okay.
So
Yes.
this is an indication
Does.
that despite being as metal poor as -3, this could actually be a member of a disrupted globular cluster.
Okay. Okay.
However, kinematically or dynamically identifying this to a potential host cluster is difficult because we don't really find clusters as metal poor as -3. So it
True.
could be something in the early galaxy that was there and have now disrupted.
Yeah, this one got tossed. Mm-hmm.
Yeah.
Okay. Interesting. Very cool. Okay. So there's our lone wanderer there, we'll call it. And CMEMP stars.
Yeah. And we discussed of CMP stars like a few minutes ago.
Mm-hmm.
Here we look at the new CMP stars we find in this study.
Okay.
So CMP stars again could be of different classes. The group one shown here is like CMPS, that is carbon enhanced with a S process contribution, the slow neutron capture.
Okay.
That is not something we are interested in for this project because that is resulting from binary mass transfer from an AGP component. We
Okay.
want to look at the intrinsic carbon values, which are coming from group 2 and group 3.
Yes, and then
Group 2 again scales with metallicity,
mm-hmm. Yes.
whereas group 3 doesn't show any scaling with metallicity and are the most exciting candidates. One star that is very close to the edge here of group 3 is a candidate to be a group 3 member. However, it falls like in the gray area between group 2 and group 3.
Yes, right here. Mm-hmm. Okay.
Yeah.
Yes,
We
well, there's
try
a
to probe
graphic on
further
there.
to investigate whether it's a true group 2 or a group 3 member using the light elements, for
Okay.
example, sodium, magnesium as a function of metallicity and carbon. Group 2 should scale with these values, group 3 shouldn't.
Okay.
Again, this star is again in the bottom panels, you see it falls. It could be classified both as group 2 and group 3.
Okay.
We couldn't really confirm whether it's a bona fide group 3 member, but we've leave it out as a potential group 3 candidate.
Fair enough.
However, we need nitrogen and oxygen to look at its true intrinsic abundances and
Okay.
then decide what it could be associated with and what could be the reason that it is an outlier here.
Right. Okay. Very cool. 2, 1. Okay. And then, dun, dun, dun. Yes, that one's a mystery. Okay. TBD.
Yeah.
Very cool. And want to sum up?
Yeah, to summarize, like in this study, we have studied around 45 very metal poor and extremely metal poor stars from the R-Process Alliance fifth data release. Here in the fifth data release, we look at the faintest members of the collaboration and
Good.
look at the metal poor end. And there we find three new R1 stars, four new R2 stars, three new R1 stars, one limited R, five CMP stars. These
Cool.
are all not very straightforward to find and are very good candidates for follow-up
Cool.
to try to understand what could be the nucleosynthesis sites. We classify uh, we classify these elements on the basis of their abundances. We classify these stars on the basis of their abundances into different groups. We try to use alpha and iron peak elements to understand what could be their progenitor supernovae.
Okay.
We try to use the different groups of alpha elements to look at their interplay to derive the contributions from the mass of the supernovae. We compare alpha elements with the R process elements to
Mm-hmm.
find what could be the progenitors for these stars and how the evolution of our process could have taken place over the galactic timescales, whether it scales with supernovae. We find there is a rise in our process as the universe gets older. So there is more europium than magnesium for a given metallicity, and that difference increases as Fe over H increases as the universe gets older.
Okay.
So there must be a primary source of R process and a secondary source of R process.
Okay. Okay.
And also we find the R2 stars scales better with neutron star mergers, and there could be dilution factor at effect to understand the formation of the R1 stars.
Cool.
Also find new members, new candidates for globular cluster escapees that indicates
Got one.
necessity to lower the metallicity floor for globular clusters. And we find new CMP stars, which have always been historically interesting to the community.
Indeed. 5 new ones.
Yeah.
Very cool. And I'll ask about that in a second. Very cool.
And the upcoming work from RPA would be something very exciting. We have like 2000 snapshot spectra that will blow over all the statistics we have right now. So we are
Nice.
patiently waiting for the next release that will be much, much higher in number than the current one.
Okay. That was sufficiently tantalizing. Okay. Very cool. Very cool. Avrajit, I want to thank you so much for walking us through your very awesome APJ supplement article. Thank you.
Yes, thank you for having me.
Sure. And you kind of touched on it a little bit there at a couple of points as went through. And let me ask it this way, in where do you think we go from here given the published article? Are there additional wavelengths outside of optical that might be useful? Can we go into the ultraviolet or the infrared to pick up something or other elements that we can't
Yeah.
otherwise pick up in the optical? And then, of course, additional surveys. And then we have this tantalizing hint of,
Yeah.
of a sixth release coming soon, which will be very awesome. So in general, where do you think we go from here, given
Yes,
the
certainly. Going beyond the optical is certainly a very good avenue that we are currently looking at. Like
Mhm.
Ian Rodder in 2022 had an article that looked at the UV abundances for our process enhanced stars using the HST,
Okay.
STIS. And
Hmm.
that was for the first time deriving a template for our process that is not derived from solar abundances.
Yes.
Now the template is derived from the values we find in the sun, but this was the first estimate of a template that is not using the sun, but are real observations
Okay.
for our process enhanced star.
Okay.
However, we need to look further and probe into the more metal poor end, because that is where we can find signatures of pure R process. So we need to find more metal poor stars and try to look in the UV as well as optical.
Okay.
Next thing is we need to look into statistics. We have roughly say close to 100 or 200 stars that are moderately or largely enhanced in our process.
Okay.
However, the more number of stars we find in the metal poor end, the better statistics it's going to give us. With
Hmm.
this new upcoming data release, that's going to be like close to 2000 new stars. That
Wow.
is going to be revolutionary
Yes.
for all our understanding of our process, nucleosynthesis.
That's
How do they come and where do they come from?
very cool. That'll be very awesome to see. That forthcoming article on 2000 of these things. So yeah, that'll
Yeah.
be things by an order of magnitude or so. So yeah, very nice. Very cool. Very good. All right. Well, that will do. So Avrajit, thank you again once more
Yeah.
for all of your time and patiently explaining that. Very nice.
Of course, thank you.
Sure. And that will do, everyone. And I hope this made your astronomy day, your metal poor astronomy day, just a little bit better. And we will see you on the next one. Bye-bye.